In virtualization, that volume is now consumed by multiple virtual machines, each of them having their own disk. And each disk has its own set of blocks that it addresses. So each VM essentially pulls data, puts data down that is hot in the context of that one VM, but not necessarily hot in the context of the whole volume. So as a result, cache is fragmented very, very easily in a virtual environment. So you need to build very large and deep caches to be able to sort of guarantee any kind of performance in virtualization. The problem with VDI, though, is that read caching doesn't help. It's an 80% write environment. 20% read, 80% write, mostly small block. So you can throw a lot of cache at it, but it's not going to use it for anything useful. What you really need are a set of techniques and tricks to handle all the writing that happens. And so a lot of our technology is really built around that, being able to handle write performance in a very elegant, high performance way with a lot of data safety and guarantees. I'll probably sort of jump into some of those pieces and talk to that. One of the things that Toby didn't mention during his demo was that the Atlantis ILIO data stores that are powering that system, and that's, by the way, typical of any environment. You can go to our customers, small, big, somewhere in the middle, and that's the configuration, 2 vCPUs with about 60 to 80 gigs of RAM. The average latency is about 800 microseconds. Okay, that's the average latency of that data store. And there's an interesting exercise that you could do over there, which is if you try to buy storage that gives you about 10 milliseconds of latency, that's pretty cheap. It's tier 2. And if you wanted to get to about 5 to 2 milliseconds, you start to spend some serious coin at this point because you're buying a tier 1 storage system. But if you wanted to start to go from 2 to 1 milliseconds, the only answer you have today is an all-flash array. And if you wanted to get sub 1 millisecond, right, for all application I/O, the average latency being in the microsecond range, we're talking about scientific computing, high-performance computing, InfiniBand, that kind of infrastructure being needed for you to do that. And you do that for a very small section of your infrastructure. You do it if you're a bank for your high-performance traders, that sort of thing. You wouldn't do it broadly across the entire data center. The promise in the power of USX really is that we are commoditizing performance. It's the end of performance as a game that customers pay money for. Capacity has gone to zero. I mean, today you can get tons and tons of capacity for virtually nothing. What you really pay for is performance and availability. That's the storage game. What Atlantis USX does is it makes both of those software functions, software-driven functions, and as a result, they become very, very elastic. And the cost of performance goes to zero. When you can get microsecond latency for every application, you don't care anymore about what the application consumed in terms of IOPS, what the architecture of something is. You're not sitting and doing prescriptive architectures to fix a problem anymore. You deploy and you consume and you scale. So, this is the end result of about 10 years of thinking and about 4.5 years or 5 years in some of the largest data centers in some of the banks that Bernard talked about, JP Morgan Chase, in the US Army, in CIA, NSA. We've been in all those data centers building and tweaking the technology to be able to really provide this real promise of software-defined storage, right? So I'll come to those pieces in a bit, but let me start by introducing myself. I'm Chetan Venkatesh. I'm the CTO and founder of the company. Bernard and I have been building this company since 2007. I started Atlantis in 2006 after an epiphany of sorts. This is my third company. I've done 2 before this. The epiphany was really simple. I found that whatever we were doing with storage was being done at the wrong end of the pipe. It was being doing at the absolute worst place that you could do it, which was on the storage controller. When you look at a storage system, it's nothing but an x86 box with a bunch of disks. It's really the software that differentiates it. And so I started to scratch my head and ask myself, really, what does it take to bring a lot of that intelligence that we claim is in storage controllers onto the compute end? Because naturally, it makes more sense to have storage virtually present there because it's right next to the application. And you can start to soak up a lot of these residual compute cycles that are sitting over there being unutilized. I mean, Moore's law gives us twice the number of cores every 2 years, and we don't know how to put it to work. And so that was one vector of thought. The other vector of thought really was that RAM was increasing, probably not at the same rate as Moore's law, but it was, the capacities were increasing. And RAM has some brilliant characteristics in terms of performance. There's really nothing faster than it, and it sits in the best place on the board. It sits right next to the CPU. So there's no faster way to get data to the CPU than to put it in RAM. And well, RAM does have 2 minor problems. One, it's volatile, so you can lose your data if you lose power. And again, the amount of capacity that you have in RAM really isn't very significant compared to what you have on storage systems. So the genesis of Atlantis really was in 2006, sitting down and asking, is there a way to use all those CPU cycles that we have to do something clever with the RAM so that it becomes an actual viable storage medium. And we've been pursuing that vision in this company for the last 4.5, 5 years now. It took us 3 years to build a really viable product, something that worked, because as you can imagine, this is all new stuff. It's one thing to be able to spin up a RAM disk and put Quake or Windows on it and run it and show it to your friends and say, this is really cool. It's a completely different thing to say, we're going to build an entire data center out of bits of RAM that are floating around your server. So that's sort of been the vision that we've been pursuing for the last couple of years. But if you fast forward from 2009, when we took the first release of our software, to 2014 today, there's approximately, I think the number is something like 20 petabytes of virtual storage that Atlantis provides across maybe about 520,000 VMs globally, in these 460 customer environments. So just reflect on that number, 20 petabytes, because that is a significant number. It's not a small number. In fact, if you were to take all the other flash vendors out there, the startups, start taking everything they've sold since they started, and you added up everything that they've all done, that number is not in the 20 petabyte range yet. And here we are, Atlantis, in VDI, which is the proverbial next year's big technology. It's really not seen the jump or ramp. We've already deployed that kind of software. My earliest customer, and I'll talk about JP because I think that's the one that we can really talk about a little more freely. This is a customer that very early on realized that the VDI game was an IOPS game. And the analogy is very simple. We're doing VDI, and we're replacing a crappy PC that my users hate with something that's going to be even crappier, simply because the PC I am replacing has a hard disk with 100 IOPS, and I'm now giving them a VDI that is sized for 20 or 25 IOPS. So I have essentially doomed myself to failure from the onset with this flawed thinking that a shared resource somehow will compensate by averaging out the peaks, right, and providing this kind of IO. So what they needed was a different strategy, because JP was thinking, how do I get to 100 to 150,000 desktops, a third of my firm on VDI? I need a strategy that changes the IOPS game on its head. And that's really where we come in, because what we do is we take IOPS and make it a function of compute, not a function of the kind of drives you have or the number of drives you have. And as a result, you really scale by adding more compute. You add more performance to your applications, and you scale out and deliver performance, availability, and all these features that you've been buying from storage vendors, just as a piece of software attached to the hypervisor. So our vision really was never to build a VDI product. In fact, as Bernard said, we started out building a server product, but with RAM. And so when we first brought the product out, there was a perception issue that, there's this tiny little company in Mountain View that wants everyone to use RAM, and so we didn't get taken very seriously as a result. There were not many people willing to put their Oracle databases on RAM, let me put it that way. VDI happened to be a great use case because people were used to rebooting their Windows machines or, rebuilding them if they broke. So the perception of the customer was, I need IOPS, this thing gives me a ton of IOPS, and if there's a volatility issue, that's not a big deal, and it's just a Windows VM. And so that sort of became a sweet spot initially for us, and we built that over the last 4 years into what it is today. 2 years back, something interesting happened. We started getting clandestine reports that our customers are using our RAM technology to run server applications. And so I had customers, and we started to poke around a little, we'd find out that customers were running small departmental databases, or they were doing test and dev. I had one customer whose Exchange storage system fell over. It was a filer, it fell down one day, and he took the whole thing and put it on a gigantic ILIO, right, with a lot of RAM. And of course, I sort of threw up in my mouth a little when I heard that, because you've got a company's whole email infrastructure running on something that we don't officially support. But it really got us thinking that maybe what's happened is we've crossed the chasm. We've crossed the chasm of people distrusting or having a perception about RAM as a storage medium, and we're at a point now where really it can become the underpinnings of a storage infrastructure in the data center. So that's really how the journey's been for us over the last couple of years. And we've focused on 3 things, and everyone's got a vision slide, but I'll just bring your attention to 3 things. We really focused on how do you take everything and virtualize it. How can a storage fabric support anything that can be virtualized and everything that can be virtualized? From desktops to web servers to applications to cloud applications, everything. Number 2, we focused on this, which is at the heart of what we're trying to do: decouple the application from the storage system. With VMware today, we take it for granted. We don't even think about it, but the application is completely decoupled from the tin or the metal that it runs on. But underneath it is a very specific storage system for that particular application. If you have a database, you probably have a VMAX, or you have some sort of a flash array to give it a certain level of performance. If you have a filer, if you have file services and you're running VMs, you have some sort of a filer that has some caching, etc. So you're plugging in specific types of storage systems with definitions that your application requires. So while we've abstracted the compute layer, our storage system is still very, very siloed underneath it, plugging into the applications. What we're very interested in with USX is completely decoupling that relationship between the application and the kind of storage it needs to run on. The application should just run on a storage fabric, and the storage underneath it shouldn't really matter. The storage capacity should come from that underlying layer. The actual durability of that data should go to a physical storage system. But beyond that, availability, performance, those are things that can be driven by pure software. That's really what the heart of the USX model is. And finally, we focused a lot more on this automation and provisioning and building, orchestratable APIs in the whole product. When you're doing, 20,000 desktops or 50,000 desktops or 100,000 virtual machines, there is no console on earth that can help you manage that. What you need is automation. You need APIs. You need to be able to hook into different types of systems and call workflows from there. And so we've brought a lot of our experiences in all these large enterprise accounts over the last 3 or 4 years in a USX, and every single thing that you can do is completely instrumentable through a REST API, and that allows you to scale it out in some very, very interesting ways. We'll show you some of those demos in a bit. I'll talk a little bit about what the underlying storage pieces that are different between USX and conventional models are. I think this is probably the heart of the conversation. So a lot of the questions you might have, I can certainly take them and start answering them over here. Yeah. What I have over here is a very, very simplified representation of what the storage stack for an operating system looks like, right? So this is the operating system storage stack. You have some sort of an application running on that. It could be a database. It goes through certain APIs that the operating system provides to read and write data as a collection of streams. There's an I/O subsystem underneath that essentially delegates different levels of specialization to different pieces. So for example, the I/O subsystem usually consists of some sort of a virtual file system layer that allows you to have different pluggable file systems. This is certainly the case in the Unix world. In Windows, we're slowly starting to warm up to this idea. For example, in Windows 2012, you can have NTFS, you can have REFS, you can plug them in and out, and that's really because of the virtual file services layer, which is an abstraction again. And underneath that, you actually have a real file system. And what the file system really does at its heart, as you know, is it's simply an accountant. It essentially keeps books about what data belongs to what collection of things and where it actually resides. Where it actually resides is delegated down to the volume manager and the partition manager that actually move data back and forth between the file system and its physical representation on the storage. And the beauty of the Windows model of the Wintel architecture is that we have this very diverse set of device drivers that allow us to literally take any kind of storage, any kind of peripheral, and plug it in as long as you can expose the peripheral's capabilities through a standard set of APIs, through a port driver, a mini driver, and a class driver into the storage subsystem. So this is how it's been built. And if you look at the evolution of Windows over the last 20 years, there's been very, very little change in this model. In fact, last year at Briforum, where I was speaking, we looked at the mainframe, the first real interactive computer, the RAMAC, released in 1949 or something like that, and it looks strikingly like this even back then. Now, when we do virtualization, what we're doing is we're putting to work all these compute cycles that Moore's law keeps giving us. In fact, if virtualization wasn't around, there would be absolutely no use for Moore's law. It stopped working for us on the PC. I mean, it doesn't matter how many cores you have on the PC. You really don't have anything better to run anymore, unless you were doing some form of exotic scientific computing or something like that. On the server side, though, it has a lot of merit because you can now carve up those CPU cycles into this concept of virtual CPUs, and you can emulate and you can basically run multiple virtual machines. And so what we've done is we've taken that previous layout, we've virtualized it on top of a hypervisor, and it now looks like this. Each of those boxes really represents one virtual machine and its I/O stack. And if you look at the I/O stack of the hypervisor itself, it looks exactly like this. It looks pretty much like this. So we've got virtualization. And if you were to go and ask the question, what is in the hypervisor? You've got something that looks pretty much exactly like whatever has been running in the last 20, 25 years. And the challenge we have with that is, and this is something that nobody talks about in the industry, we're trying to make things go faster and faster by working at one end of the system, which is plugging in faster things over here. But as you start to look at the modern day data center with higher levels of densities of VMs running, you find that our operating system architectures haven't changed fundamentally. So the storage subsystems haven't changed, and every storage system uses a series of locks and queues to essentially traffic data down to disk in a safe and predictive way, right? So the I/O subsystems, for example, use extensive locking to make sure that an application that is reading or writing some data, it doesn't change while it's working on that. There are multiple queues that are implemented through the volume manager, the partition manager, as data gets shunted from multiple applications in a very, very orderly way down into the disk. So you don't change the write ordering, you don't mess things up. And finally, this is also implemented down at the storage level, where the storage controller itself will have its own locking and queuing and so on and so forth. So when you start to do virtualization on the hypervisor, all your guests are performing at the application level all of this locking and queuing. And then the hypervisor underneath it, which does a fantastic job of actually scheduling your CPU and doing a good job of sharing the CPU resources, does a poor job of actually scheduling I/O for you. And this is, why do we have a storage challenge in virtualization? Is because the hypervisor simply does not have a good enough way to deal with the I/O that's coming from many, many different types of disparate guests. Right? A database is doing different things from the way a web application is, which is doing different things from the way the VDI VM is. As far as the hypervisor is concerned, it's all just a bunch of blocks that are being requested to be read or written. So it does what any good government does when there's a great demand for services that it can't really dole out. It essentially gets very social about it and decides to fair share whatever resources it has. And essentially, the hypervisor then plays the role of trying to give you as fair a chance of being able to read and write from the underlying storage system as possible, right? Now, that's well and good when you've got, when you're in 1998 and you're doing 10 VMs on a server, right? You have a fairly big time slice to share with all your VMs, but fast forward to 2014, and people are concentrating 45, 50, 55 machines on a server in a test and dev environment. In VDI, they're putting 100, 120 VMs per host. The band of time that the hypervisor has to share among all those VMs is literally in the microsecond range. And as a result, it cannot schedule I/Os effectively. The other problem, and I'm getting really deep and technical, and I hope I don't bore you in this process, is this. This is all a game of cards. This is charade. This is smokes and mirrors. That's what virtualization is. Each of these systems thinks it's running on a physical disk. Each of them has a HBA that is 32 slots or 16 to 30 slots, 32 slots deep. The physical exit point out of the system is also a HBA that has 16 or 32 slots. When you have 100 VMs running over there, right, that's 32 times 100, 3,200 queue depth, potentially queued and waiting, all waiting to go out on a 32 slot depth. So the question I have for you is, when you've got this kind of a scenario in a data center, and the vast majority of challenges we have is in the way that the hypervisor is managing storage, what sense does it make to take a fast flash system and plug it in over here? It doesn't make any sense. What you really need to do is to start to rethink how you do I/O within a hypervisor. And that's really what we've been doing for the last 2.5, 3 years around the USX product, which is really building an in-memory storage technology that is not a RAM disk, but is a complete storage subsystem that can be nested in a hypervisor that eliminates all of the challenges of this within the hypervisor. Now, because of where we insert ourselves, we don't change anything. We don't change the way the guests behave. We don't change the way the hypervisor behaves. So you still have the penalties of the locks and queues at the guest level. But the hypervisor itself becomes a very, very efficient, lean, mean, performing machine when it comes to delivering I/O because of what we've built into this layer. So I'll talk about that piece next.
You have a pretty interesting scenario, though, when you, at a high level, it looks you're going across a broad set of hardware platforms underneath, and ultimately even every single one of them may have multiple points of failure and protections at those layers. But effectively now you're presenting a large pool of storage on multiple platforms. You have multiple points of failure in that area. So especially presenting as a VM, what are the risks that come into loss of access to the VM, pathing to the VM, pathing back to the hardware side? If you have partial loss and you suddenly have this broad storage pool that loses 1/3 of itself because of lack of access, because of a hardware failure at the storage level layer, right, then how do you deal with that? Because ultimately, while you say that, why would you put flash in there? Well, there's a reason why we put flash in there and why all those storage vendors are doing it, because it is getting huge optimizations and gains. Not to discount what you're doing, but at the same time, the failure scenario is much more.
It's more interesting, let me put it that way. It is more unknown, and I think we tend to fear the unknown more than we fear the known, right? So I grant that it's a lot more unknown in that. But it's not really, because in fact, if you ask me where we spent the majority of our year and a half, it was dealing with that. So we've had to build our own HA technology into every layer of our product to deal with path level failures, to deal with aggregate level failures, and to deal with volume level failures. Since we're presenting a continuous, highly available storage volume to the application, we need to be able to flip-flop between nodes in a data center that might themselves be on these networks that have these transient losses over time. So how do you start to compensate at the software level for a lot of the kind of organic noise there is in a data center environment? We've had to build a lot of that into our technology. I'll cover those pieces in a bit, but that's a really astute observation. You are trading one thing for another. I'm going to argue that this is really how you get to this data center of the future. This is how the future of storage looks like. It looks less and less like you buying a big box, sticking it in a cupboard, and then rolling a cable out from that into your server farm. And it looks more and more like this, where you have some boxes that you bought in the past, but more and more you're just buying clever software and you're using stuff that's available on the server to build shared storage virtually. Yeah.
What are the kind of ratios that you'd look at as far as RAM comparison to underlying hardware, traditional spinning disk storage?
Right. So we typically look at a ratio between 80-20 and 60-40. Okay. Now those are what we call post-optimization ratios. Remember that I think the big differentiator from a technology standpoint between us and every other storage system out there is that we provide, or we perform our storage optimization, which is deduplication compression, as the first point of ingest. As soon as data comes into us, that's the point at which we optimize it in memory. Okay? And so subsequently, everything that we do from a data preservation, protection, and availability standpoint is done with deduplicated payload. That means essentially redundant IOs are eliminated, and only data that needs to be persisted, committed down, then needs to be protected and replicated and shared across. So that's one big factor. Simplistically, what that means is if you had a cache that could store 100 blocks of data, because we can deduplicate and compress up front, we can pack 5,000 blocks of data on those 1,000 blocks. So we get an amplification as a result of that, right? In highly homogeneous workloads like VDI, our reduction, and that was a question asked earlier, our reduction is about 95% for stateless workloads. We can essentially turn these big fat VMs into small megabytes of data because of that level of redundancy. In less homogeneous workloads, that ratio is about 75% for SQL databases. It's about 80 to 85% for email and exchange, for example. And then there's a whole class of stuff that doesn't do well under it. For example, video streams. They're already highly compressed and there's very little redundant data. So you shouldn't be putting that over there. Yeah?
I was just going to ask, ZFS and my Nimble do compression on the front end. And that's how they deliver higher IOPS. And they're very dense storage systems. So the answer to your question, why plug in an array to this stack? I've been through that question myself, and it's like because we have to economize. It's not everything's going to get the best.
But I would suggest to you that the constraints that they have are horizontal and across all storage systems. That ultimately a Nimble is no different from a Pure, except with some incremental advantages in compression, etc. But there's no broad philosophical change between one storage array and another. And that's the essence of the innovation that we're trying to talk about over here. An incremental version versus something that is sort of in many ways a brave new world and a great leap forward. I'll come back to that piece. I'm trying not to sound like an ass, but sometimes I do. But so bear with me.
One of the things, the software-defined storage space is obviously getting crowded.
Yes.
I mean, there's a lot of players there. We have Nutanix, we have Simplicity, which you could argue whether they're software-defined or not because of their hardware card. But then we have companies like Maxta and things like that. How would you differentiate yourself from? I mean, obviously, you can say you're software only where Nutanix isn't, although they really are. I mean, because they're looking at hardware. Their hardware is all commodity based.
Yep.
But what about like a Maxton and things like that? How do you differentiate yourselves from those? Is it the in-memory side of the house?
I think there are a couple of points of differentiation. One is the way we are leveraging RAM as a alternative to flash, right? We can use flash, by the way, certainly bring everything that we do on RAM on a flash, but there's RAM available. And the vector of the industry is towards doing more interesting things with RAM. For example, Diablo's memory channel architecture, you know, non-volatile RAM from memristor technologies, all of that. That's happening in the next 3 to 5 years. So we think RAM becomes far more interesting as a foundational storage technology compared to flash, because flash ultimately doesn't have many of those benefits that RAM does. So yeah, using RAM is one big part of our overarching strategy. The second area that we're very interested in, and compared to Nutanix, is I don't want to replace anyone's storage. I don't want to go in over there and say, get rid of that and put this in. What I want to help you do is optimize what you have and optimize what you will buy in the future. And hopefully help you buy for capacity rather than have to buy for performance.
But would it be safe to say that over time, you would see an Atlantis solution sort of beginning to supplant some of those existing storage systems in favor of more direct attached storage for simplicity and just because of the benefits you talked about?
Perhaps, you know, but ultimately when I talk to customers today, I mean, just this is in 2014 and possibly for the next 2 years, what they're saying is that they're essentially their virtualization environments are, you know, ballooning. They're going from 50 to 40 or 50 to 70% virtualization, and that means they need to provide storage infrastructure to drive all of that. And if they can get more out of what they have today, or they can spend less instead of spending a lot more, then those are things of a great deal of interest for them. And so several of our beta customers, for example, one was a very large bank. This particular customer has a moratorium on storage spend for the next 2 years. CIO said, I'm not buying any more storage, we're done. Our utilization levels are shit, they're like 18 or 20%. But you guys keep coming and asking me for more and more storage. And then you keep telling me you've thin provisioned everything and that there's an axe in your head. As soon as the hydration level gets to, I don't know, 55, 60%, I need to buy more storage. And so he basically told them, go and find a way to get more efficient, right? And this customer, this is a complex scenario. They have about 6 or 7 different types of arrays from different generations of procurement, right? And they need to reclaim across all of that. This is a software solution that works horizontally across all of those pieces, right? Now, if they want to expand that with a little bit of converged storage by attaching DAS, they can do that. Or if they want to bring in a big data application to do real-time data analytics, they can do that. I'll come to all those use cases in a bit, but the point I'm emphasizing, it becomes less and less important what the type of storage underneath is, what the characteristics of the storage is, because all this intelligence is now, you know, up at this layer.
Well, let me ask, this might be a stupid question, but I'm going to ask it anyway. So I've got an array from Dell, I've got an array from EMC, and I've got something else sitting out there.
Yeah.
Do I add additional complexity when I start putting the Atlantis solution in place, or do you replace that entire multifaceted management paradigm with your own, or do I still need to individually manage those units of storage as well?
Yeah, so in today's release, in what you have today and what you will have for the next 12 months, we're not trying to change the way the customer manages drastically. So today they interface into VMware by exporting a LUN from those SCSI systems, from the block storage. So it still comes in as a LUN. Whatever storage you want USX to manage comes as a LUN into ESX as a data store, but we exclusively consume that LUN. None of the applications consume it.
Accelerate it with your in-memory technology?
Exactly, and our in-memory sits on top of that, and now it completely changes the characteristics of performance. And I'll show you a demo for that bit in a bit. Yeah.
The premise, though, is that you're trying to get the data that's on your storage closer to the application, so you're moving it up in the stack.
Yeah.
What happens if the server
fails?
Itself fails. You still have to go down the stack to make sure that it's available for some other server to be able to use it.
You have to write it back.
I'll come to that piece. I actually got slides on that, so I'll talk about it. So what we did was, I'll just sort of rewinding. This is what that stack on the hypervisor looks like. We've replaced it in USX with a stack that looks like this. This is our software plugs into the hypervisor, and instead of having all of that, right, essentially provides an I/O subsystem, a very, very lightweight file system with just enough POSIX compliance to fool whatever's consuming it and thinking it's a real file system. And underneath it, a full set of data transformation, data optimization services running all in-band real-time on the hypervisor.
That red box is key. I mean, so basically we're getting rid of the data protection scenarios we have in our existing environment, and we're going to use your replication-based data protection methodologies, right?
Right. Now, in the current version, what it does is it very smartly says, if you've got a SAN underneath this, you already have data protection over there. You might be doing RAID 6 or RAID DP or something like that. So this is intelligent enough to essentially provide replication for memory contents and local disk contents. But if you're using shared storage underneath, delegate the protection down to the storage itself.
Can you tell it not to?
You could tell it not to as well.
Okay.
Yeah, you could tell it not to as well.
You still can't commit the write until it gets down to the disk subsystem.
So that's where it gets really interesting. We've got, and this is really our range of patents, right? Our range of patents really talk around how, there's I'll sort of back up and say, the only way to get faster is to get closer to the application, right? Or spin the disk faster. And those are sort of physical things that you can do. But if you really want to get cute and clever about it, if you can change the write acknowledgement or placement, where you do your write acknowledgement, based on some intelligence, you can dramatically change the game. So what we do is we exploit our deduplication and compression to try and do as much of the write acknowledgement over here and over here once it's been replicated across. So the primary acknowledgements always happen in memory as soon as a certain number of nodes have already received the data. In memory again, okay? Now we also take advantage of what data is duplicate, what data is unique, and the transientness of the I/O. For example, we have a heuristic in the I/O subsystem that watches how blocks change over time, individual blocks, and looks at the rate of change of a block and decides whether a certain range of blocks needs to be committed down every few microseconds, or maybe every second, or maybe potentially every 10 seconds. So we have built a lot of that heuristics to change when the write acknowledgement needs to happen. In the worst case scenario, you will make an I/O acknowledgement for a very small domain of I/Os when it hits the physical disk subsystem. But for the vast majority of I/Os, the acknowledgement happens right up there. That's how the latency guarantees come about.
Okay, but if you are guaranteeing the I/O that high up the stack, isn't there potential for data loss?
Yes, if you have a data center wide loss, right? Because one of the things that we have is the ability to basically place our bits of data on multiple servers, on RAM of multiple servers, because we're pulling it across, right?
Right.
So from appliance to appliance to appliance.
So
it's spread out. It's
when
basically
I looked at other software-defined solutions like this, basically they acknowledge the data, they acknowledge the I/O after it hits disk.
Yes.
So yes, their latency figures are worse, but their data integrity is great. So there's no risk.
Let me walk you through one more bit of it. Here's the whole gist of it. If you look at all these other guys, right? They do their data deduplication and compression as a capacity optimization technique.
Right.
I do it as a performance optimization technique. Big difference.
The more you can deduplicate your RAM, the more you can cram in that RAM.
Yeah.
I get
and
that.
the less I need to replicate.
And other people do that as well.
And the less I need to replicate is the point I'm making.
Right.
Also, if you already know that a duplicate piece of data is on disk somewhere, you can acknowledge it with no risk of data loss.
Absolutely.
Right.
I'm worried about new data that's not already being written.
Yes, exactly. New unique data being written is...
Well, when it comes, like I said, the worst case scenario is if you have absolutely new unique data that has never been seen across a node, right? The penalty you will pay is of going down to disk on that. Subsequently, if that, because when we talk about new data or blocks, etc., right, there is a very important subtlety over here. We have to talk about whether it's a new block being allocated or is it the same block being changed with new data. There's a sort of, there are different gradations, right, of this particular conversation.
Yeah.
I want to summarize it as saying the software has the intelligence to target each and every one of those specific scenarios and do the right thing from a data protection standpoint.
Okay, so if it's brand new data that's never been seen before, it's going to acknowledge it after it writes it to disk.
Yes.
Not once it's up in RAM.
Right.
But if it's something that's already existing in the environment, you're going to acknowledge it in RAM because you got a pointer out there already for the deduped block.
Right.
Okay.
Yeah. So in a nutshell. So now, we haven't changed the game over here because that would involve rewriting the application, but the I/O stack within the hypervisor fundamentally changes and allows you to make all kinds of interesting new guarantees on application performance and latency and things like that were not possible
Chetan,
before.
I know you're about to be pulled off with the big shepherd's crook, but one of the points
New Zealand.
in one of your diagrams, you dropped out the stack between the virtual machine going through the hypervisor to get to ILIO has just disappeared.
Yes. So what happens is we've changed what we provide as an NFS-based service that we have essentially tuned for the in-memory characteristics. Sure. So NFS intersects with the hypervisor completely different than a SCSI-based stored subsystem does. Yeah. There is no queuing and locking. In NFS, in ESX especially, it's implemented as just a big queue. In fact, you can set that queue depth to something ridiculous in ESX settings.
Yeah.
So you create a massive queue on the NFS client, have ESX chuck all its IOs in there in whatever order it gets them, and we take it from there, and then we optimize it and we deliver it down.
And that access piece is locally within each ESXi server where you're running the
Exactly.
appliance.
Exactly.
Right. That drops the latency out.
NFS works with...
Yeah, I'll come to this, guys. I need to really cover this part because this is the heart of it, and forgive me for rushing through this, but this is what we can do. We can take different types of storage resources, SAN, NAS, and DAS, and different types of local server resources like RAM and flash, and pool them, right? And build what we call application-defined storage volumes, which are virtual storage volumes that emulate a certain type of characteristic or profile that you want. So we have 4 volumes in the product today. You have something called hybrid, which is, do you really love Nimble and you would like to spend a lot of money for that? Well, what if you could build a Nimble on the fly by walking through this wizard? That's what it does for you. It essentially allows you to build a complete hybrid storage array in software by simply taking whatever SAN, NAS, DAS you have, layering RAM and flash on top of it, and providing you with a storage volume that looks like a hybrid array. You can also build a redundant in-memory storage layer for big data applications, for applications that need very, very low latencies and that you want to transact very, very quickly on. You can also build a persistent version of that simply uses a delayed commit cycle to take whatever's over there and logs it down a disk. Right? This is really, really useful for applications like Cassandra, for example. And finally, you can build an all-flash array just using local flash or just RAM. And what is not covered over here is just, it's implicit. You can also build a converged system like Nutanix or SimpliVity. It's a part of the software. So you essentially have wizards or software consoles or even REST APIs that let you build any kind of a storage system virtually in your data center without actually having to buy it and wheel it in and do all of that. What does this mean? It's a pretty big thing because if you look at the industry today, there's a religious war saying my SDS is the one true SDS. And it's the most ridiculous conversation going on. My converged system, my converged compute system is better than hybrid, blah, blah, blah. Every system has its use case. And what we're giving the customer is this ultimate choice to build the software array virtually for whatever type of application they have. And that's how you get all these applications that don't play well, holding hands and singing kumbaya on the ESXi, because the underlying storage layer is completely virtual.
So why do you have Atlantis USX and VMware vSAN if you can build it yourself?
No, I like vSAN, and one of the big things that we've done from early onset was to say, let vSAN do the aggregation of local disk. We can bring the NAS and the data services on top of vSAN. In fact, that's what that paper over there is. In a VMware environment, you're going to find that vSAN is very easy to enable in those environments. So from a customer standpoint, it's a no-brainer to use vSAN.
Of course.
So by putting us on top of vSAN, you get better performance, better capacity, but also the ability to bring shared storage resources that vSAN can't leverage today into that mix. So that's how we look at vSAN. We don't see it as a competitive situation. We really see it as something that's complementary.
But you could build it yourself with...
Yeah, that's a really good question because it looks as though you're actually layering an extra piece of licensing on top when effectively you could use that storage, that flash storage and raw storage pool at the DAS layer, just roll it into USX and treat it as part of the USX platform rather than pay for vSAN underneath it when the platform itself is already...
expensive also, right?
It could be, and I'm not familiar with the pricing, but yeah, you could do it one way, you could do the other. Our philosophy is whatever suits you, and we think there'll be a lot of environments where vSAN will be enabled by default, and that we should be able to plug right into. I'll just talk very quickly. So this is the hybrid storage that you can build. You can essentially take some NAS, some SAN. We can take RAM across, or if you have flash, take flash across and automatically give you a hybrid storage pools across. All of that. That could also be local storage. That's what we call the hyper-converged system. Really the ability to just use local disk and JBOD and then aggregate that, and along with RAM, again, build a very, very high performance storage system. This is very interesting, of course, to all the server OEMs that are out there. And so, we're doing quite a lot of interesting work there. And then this is actually a great example of what this means. The X6 to me sort of epitomizes the real future of what server technology looks like. This is the IBM X6 server that was announced in Jan. This thing has 60 processors and 2 terabytes of RAM. But more than that, it has 19.2 terabytes of raw local flash and flash on them. I mean, that's what we're coming to. That's the world. In 2 years, that system is your default system that you buy and put in your data center. You're not pissing around with 192 gigs of RAM. This is what you're putting in. This is what the foundational building block of your data center is. And you need a storage strategy, a product, a technology that leverages that and allows you to build data centers on top of that. And USX really has been designed from the ground up for this particular world. So big data in memory is another very, very big use case for us. By using in-memory, you can essentially accelerate all these workloads. The big challenge in big data, for example, right now is to get to real-time analytics. And real-time analytics fundamentally is a function of how fast you can drive your storage. And we can actually power a fair amount of improvements, 400 to 500% type improvements for most of these workloads by running them in memory on top of this. So I'll quickly get to the show me part, because that's really the coolest part. This is the vSAN bit that I want to talk to you about, which is that VMware Virtual SAN can aggregate the local storage, and we can bring shared storage resources on top of that and put our data services on them. And by the way, now expand vSAN's portfolio from just view and desktop to doing all these enterprise applications that customers would want. This is an actual joint effort with VMware to qualify what does this mean. We were able to deliver 117,000 IOPS on a 3-node vSAN, which by itself could do, I think, 8,000 or 10,000 IOPS. I don't know what the before number is.
Was that the first beta, or was that the second revision of the beta?
This was done about 3 weeks back, so it would be the second revision with the expanded 8-node cluster.
But I don't get why you need vSAN for this.
Yeah, I was gonna ask the same question. Why would you buy vSAN and Atlantis? It seems like that would just be like giving VMware free money.
Yeah.
You say that's a bad
Atlantis.
thing.
Because I think, I was saying that because I think what will naturally end up by virtue of vSAN being embedded in ESX, that a lot of customers will turn it on, that a lot of customers will deploy and start using it.
But
it's a separate
free,
license.
yeah.
It is. But I think it's so easy to turn on. If you looked at it, right, it's essentially a little click button.
It's a checkbox, but it's only while it's in beta. Well, as soon as it's out of beta, it's going to cost you an arm, well, maybe anywhere between 1 arm and 6 arms.
I think we should have a longer conversation about that. But I really want to get to the demos so that we can, put some real form to what we just discussed.